Mr. G here today to talk to you about diffraction, which is another cool property that you're going to find when you're studying waves. If we start off looking at this picture right here, you'll notice that there is an interesting pattern forming, that all these waves tend to be coming in essentially perpendicular to the surface, but then once it comes in, you'll notice that there is this kind of curving pattern forming once it's inside the lagoon. And the question is, well, what's up with that? So the first thing we'll talk about is a general idea where we have a wall. In this case, it's going to be the waves are passing the barrier. Well, we know that the waves are coming in as a plane wave. So the wave fronts are essentially like this, parallel to the actual surface it's going to run into, perpendicular to its motion. But once it actually hits the barrier, something really cool happens. All of a sudden you start getting this curving effect. And it looks like this. You'll notice that I'm attempting to draw the wavelengths at essentially the same wavelength because that doesn't change. But generally speaking, this is the picture you're going to have when it's running into a singular wall. When it runs into two walls, well, you've already seen what that looks like. You have your wave fronts coming in. And once it goes through the barrier, again, we're still like this. But now we're going to start to see something like this. And this whole idea here, this is what we're talking about when we mean diffraction. There's an actual change in direction, if you will, or at least pattern of how the waves are actually moving. So when we talk about this idea of diffraction, again, we look here, and I think everybody's got it pretty clear now, exactly what this idea looks like. So if we're talking about what affects diffraction, let's start off by the definition that diffraction is the bending of waves around the edges of barriers. And it can be affected by a few different physical properties. First of all, the wave speed, generally speaking, greater the speed, the less bending. And again, that would make sense. It's essentially blowing through the barrier. It's not giving the barrier enough time to affect its path all that much. Wavelength, just the longer the wavelength you have, the more bending that you're going to see. So again, shorter wavelength would be the opposite. There'd be less bending. And finally, with an opening size, if you have a smaller opening, you're going to see more bending. And if you have a wider opening, you're going to see less bending. Again, that should intuitively make sense with the idea that there's less interaction with the barrier itself, and there's more room for the wave to actually get through that barrier. So we've been talking about the idea of going through one slit. The question is, what happens when we have two slits? So again, the waves are coming in as a nice, beautiful plane wave, and we're going to get to the barrier, and what's going to happen? Well, you're going to see bending on both ends. So all of a sudden you have this on this side, and you have this on this side. Now, I will note that my curve may be exaggerated, but again, if you take a look at those wave pictures, you can see that clearly this effect is occurring. Well, isn't this some interesting stuff going on here? We've got a couple of different ideas to look at. If we look right here where the two waves are crossing, well, you've all seen this before in the interference discussion. This here is constructive interference, because now the two wave fronts are actually going to add up on each other. Conversely, you have these sections right here where you have a wave with amplitude versus a wave without amplitude. In that case, you're now looking at something that's going to be destructive. So again, taking a look at these ideas with mechanical waves, water is certainly an example of that, at least in the ocean. And now we see how those two ideas relate right here. Now, here's an example where you drop a couple pebbles in the water. You'll see that these wave fronts are going out in nice concentric circles, and you see that this one over here has created the opposite effect. So we see this in everyday life, and again, of course, these crossing are constructive. These intermittent points are certainly destructive. So in general, if we want to talk about it, when two crests meet, we see the constructive interference and a maxima. Okay, so when we're thinking of it in terms of amplitude, remember that when it was constructive interference, it actually added the amplitudes together. Conversely, in the troughs, we're seeing these ideas of destructive interference, and in that case, it's going to be a minima. When we're dealing with light, a maxima is definitely a bright spot, and a minima is a dark spot. So if we take a look at this right here, very, very classic double slit experiment done by Young, and what he did is he had this particular barrier here with the double slits, and then he shone light upon it, in this case a laser light, and what happened is, as you would expect, there was definitely going to be diffraction, and in the process he shone it upon a screen to show its actual constructive and destructive interference, and you can see here the difference between the dark patches and these light patches here. And if you take a look, you'll notice along the bright patches, that's where the constructive interference was occurring, and in the dark patches, that's where the destructive interference was occurring. So this double slit experiment was fundamental in proving this idea of diffraction existing. Here's yet another idea of diffraction, except this time we're going around a spherical object, and in this case, if you take a look, we are still seeing these dark spots here, and we are seeing these really great bright spots right there. Again, diffraction in all sorts of different scenarios. So you might ask yourself, well, gee, I've always wondered why the sky was blue, and if they haven't taught you yet, we're about to teach you now. When a ray of light strikes a particle roughly the size of its wavelength, it scatters in all directions. So again, we need light to scatter, and in this process, white light is scattered by particles in the air such as water. So you can think about light scattering through water, and in this case the short wavelengths are scattered more than the longer wavelengths. So instead of seeing something like red, instead we're going to see blue, and because of that our sky is blue. Conversely, if we're taking a look at something at sunset or sunrise for that matter, the light has to pass through more of the atmosphere, which means way more of the blue light has to scatter away, which means all we're really going to see prominently is the red light. And if you take a look at this image right here, they've got a great image showing that here's what it looks like at noon. And of course the idea that the atmosphere scatters blue light much more than red. But at sunrise, if you take a look over here, the sunlight must pass through more atmosphere. Blue light scattered away, leaving a red light. So you get something like this at sunset. So now you know when you take a look off your balcony to observe the sunset, you can say, hey, Mom, I totally know that this is light scattering. Very, very nice. Now, there is a beautiful consequence to this idea of understanding scattering and diffraction, and it comes from the question, well, why do sunglasses have such a funny reflection? You'll notice if you have a pair of something like Oakley's that you're going to see this funny, like multicolored kind of shine. And the answer comes from the idea of polarization. So to define polarization, we define it as the filtering of light so that it can only travel in one direction. So the whole concept of having, say, polarized sunglasses is the idea that we want to protect our eyes from harmful light rays. So to do so, we essentially set up a couple of grates in front of our eyes to only let the certain amount of light that we want to come through, and not just certain amount of light, but the certain type of light. So if you take a look here, this is the idea of light being unpolarized. It moves in every single direction. It's a transverse wave, but it travels in all planes. So in that case, any one of these planes is acceptable. You'll notice that it's essentially a cylinder. But when it reaches this first grate, which is a vertical grate, obviously any of these waves or those waves, they're not going to get through. They're going to hit the grate and they're going to stop, which means behind it what you're going to see is this beautifully polarized light wave, in this case a vertical polarization. The question might be now, well, what happens when it hits the horizontal? Well, we've already eliminated all of the horizontal light in the previous grating, so what's going to happen is you're going to end up with no light at all, which is why you would see a demonstration where there are two polarizers on top of each other, and when you turn them 90 degrees, you end up getting no light at all. Here's another demonstration right here. This is looking head-on at the light that's traveling in all planes. Again, it's this big, ugly mess, but when we polarize the wave, you'll notice in this case this would be vertical polarization, and it is straight up and down, giving you this beautiful transverse wave. So that should answer the question then, why is all of this happening? Well, that's just the polarization that they've added to your sunglasses to protect your eyes from any of the harmful UV rays or any other type of rays from the sun. So you've had a crash course on polarization. We talked about how barriers can actually diffract your waves and curve them. We talked about Young's double slit experiment. If you want to look more into that, I highly recommend it. It was quite revolutionary in its results. And then we got into the idea of polarization, where we are constantly trying to protect our eyes, or in the modern day case, 3D movies work on the concept of polarization. So you're set, my friends. Good luck with your homework, and we'll talk to you soon. Bye-bye.